Good evening, gentlemen. Um, Welcome to Modern Physics 1. This is part 3 of chapter 5, and I'm going to pretty much wrap up chapter 5. I might have some concluding comments, but I'm pretty much going to cover the substantive issues, and I'm going to ask you also to do a little reading. So what we're going to do this evening is we're going to actually look at Bohr's correspondence principle. So the correspondence principle sounds deceptively easy. It says that if we look at a quantum system, and if we look at it as the quantum number gets very large, in this particular case, we're looking at, say, for instance, the hydrogen atom as n gets very large, then this is going to move seamlessly over to classical physics. As a matter of fact, we kind of laid the groundwork for that in the previous discussion where we said that the Rydberg atoms, which were high quantum number systems, actually began to approximate little mini solar systems, right? In the case of hydrogen, the electron going around the proton in a almost classical orbit. So the correspondence principle is still hotly controversial, so to speak. It's discussed often. It has its quirks and its problems. But what it allowed Bohr to do was that it allowed him to show that the angular momentum was indeed quantized in intervals of h bar. So remember from the first discussion that one of the postulates was that the angular momentum was equal to n times h bar, where n is an integer, 1, 2, 3, etc. Correspondence principle actually allows us to almost derive that, right? And so again, this goes back to Bohr's original paper on the Bohr model. And so we are around 1913 time-wise, all right? So some things that are firm here so far, right? So some things that are firm is that the energy of transitions in, at least in hydrogen atom, are related by the Einstein-Bohr relationship, or Einstein-Planck relationship. Einstein-Planck relationship. We demonstrated that in the previous discussion in looking at the electronic transitions, in particular the emissions. And we also know well at this stage Maxwell's classical theory of radiation. And we've alluded to this previously, right? So so any charge that is accelerating is going to radiate electromagnetic radiation. As a matter of fact, if you have an electron in an orbit, as in the Bohr model, in an orbit of orbital frequency F, then it's going to give off, it will give off electromagnetic radiation at that frequency. Okay, so, and again, that's on the surface is not not something that one would guess, but that is indeed the case. Okay, so let's begin to set up the picture here for this problem. So so we have again for hydrogen, right? Let's just pick on hydrogen. That is Z is equal to 1. It allows us to take one more parameter out of the equation, so we don't have to carry a Z around. So we have a proton as nucleus. Here would be, n equals 1. Right here is, n equals 2. And here is now 2 orbits way out here at very high quantum number. Oh, let's get rid of that. So way out here at very high quantum number. The friction on the iPad is not the best. What happened there? So let's try that again. All right, so there's 2 orbits at high quantum number. And we'll call this R1. We'll call this R2. This is a proton. We have an electron out here in these orbits, and it's going to make a transition from this outer orbit to this inner orbit. We're going to have the release of a photon. We'll say that this electron is going around with an angular frequency of omega. We know the relationship between the orbital frequency and the angular frequency is just a factor of 2 pi, right? So these are high quantum number states. Okay. Beautiful. We know, right? We know that E total for the electron, the total energy of the electron, is going to be 1 over 4 pi epsilon naught E squared over 2R. Okay. And so I'm going to just move up the screen a little bit here. We know that the angular momentum is m sub e times v times r for circular orbit. And I'm going to recast this in terms of the angular frequency. Okay, so this is then going to be m sub e omega r squared, because v is equal to r omega. Again, if you don't know where those come from, then it's time to open up Halliday, Resnick, and Walker chapter on rotational motion to reacquaint yourself with that physics. And so what we have then is m sub e v squared over r, which is equal to 1 over 4 pi epsilon 0. This was e squared over r squared. One of the r's cancel, right? This is Newton's second law. We then have m sub e V squared is equal to 1 over 4 pi epsilon 0 E squared over R. Let's multiply both sides by R. This is going to give us m sub E. V squared times R is going to be 1 over 4 pi epsilon 0 times E squared. And let's multiply both sides by m sub E times R. All right, so we'll multiply both sides by m sub E times R, m sub E times R. Okay, this now is going to give us over here, it's going to give us m sub E squared, V squared, R squared is equal to 1 over 4 pi epsilon 0 E squared m sub E times R. This is going to be L squared. So L squared then is going to be 1 over 4 pi epsilon 0 E squared m sub E times R. And this is going to be important, but let's solve for 1 over R as well, and you'll see why as we develop this derivation. This is going to be 1 over 4 pi epsilon 0. This is going to be E squared m sub E over L squared. Okay, and let's just keep these two equations highlighted. All right. So let's go back and look at E total now in terms of L squared. So E total is equal to negative 1/2 1 over 4 pi epsilon 0. It's going to be E squared over R. This is 1 over R. So now I'm going to use this here to throw in down here. This is going to be negative 1/2 1 over 4 pi epsilon 0. This will be E squared times 1 over R. 1 over R is 1 over 4 pi epsilon 0. M sub E, E squared over L squared. Okay, beautiful. All right, so that now relates the energy to the angular momentum squared. All right. So now let me just scroll up here, give us a little bit of space. Let's take now DE total with respect to L. And this is going to be then negative 1/2 1 over 4 pi epsilon 0 E squared. I pick up another 1 over 4 pi epsilon 0, so that makes that squared. I pick up another E squared term, so that's going to be e to the 4th times m sub E times the derivative now with respect to L of L to the negative 2, right? It says L squared. These are all constants, right? So these just come on out. And so this is going to give us now, this will give us then negative 1/2 1 over 4 pi epsilon 0 squared m sub E times e to the 4th. And then that derivative now is going to be negative 2 times L to the negative 3. Okay, beautiful. All right. So the 2's go, the negative signs go, and I get that the change in E total with respect to the angular momentum is going to be 1 over 4 pi epsilon naught squared m sub e to the 4th over L cubed. All right, so let's work with that a little bit. So let's take a look at this L cubed term. So L cubed is going to be then m sub e cubed, v cubed, r cubed, and then this is going to be then L squared times L. We know what L squared is from the previous page. So then this is going to be 1 over 4 pi epsilon 0. This is going to be then m sub e squared times r times L, which is now going to be mvr. Okay. And then what I'm going to do is I'm going to multiply and divide by v. Multiply and divide by v. And then now this is going to be 1 over omega, right? So remember that v is equal to r times omega. Whoops, what did I do here? Wrong circle job, right? So it's going to be r over v. So r over v then is going to be equal to 1 over omega. Okay, so then this is going to be then 1 over 4 pi epsilon naught. This will be m sub e squared times r times m sub e. This is going to be, let's see, did I mess up here? This is going to be v squared, m sub e, v squared over omega. Okay, I think that's good. M v squared over omega. All right, so now that's going to give me, right? So I have the following, right? So let's go change up the color here. So m sub e v squared over r is equal to 1 over 4 pi epsilon 0 e squared over r squared. One of these r's cancels with that, right? This is Newton's second law. So then I could plug this into here. And then what I get is m sub e squared times r over 4 pi epsilon 0 times 1 over 4 pi epsilon 0 e squared over r times 1 over omega. So we get some cancellation. The r's go. And lastly, I get that L cubed is going to be then m sub e e to the 4th over 4 pi epsilon 0 squared times omega. Okay. All right. Wow, all that work to get that, because we need that to plug into the change in E with respect to L expression, right? So recall that change in E, should go back to white here now since we're back to the original derivation. So change in E total with respect to L was 1 over 4 pi epsilon naught squared emps of E, e to the 4th over L cubed. So now I'm going to take this, throw that into there. And then that's going to give me change in E total with respect to the angular momentum. It's going to be 1 over 4 pi epsilon naught squared. Okay. It's going to give me emps of E, e to the 4th over L cubed, which is emps of E, e to the 4th times omega. Whoops, sorry. Divided by 4 pi epsilon 0 squared times omega. And we get mega cancellation here, right? So this goes, this goes, this goes. This is the only remaining term, and it's in the denominator of the denominator, so it just pops upstairs. Okay, so it says that the change in energy total with respect to the angular momentum is equal to omega. All right, so, or, right, that the change in energy total is going to be omega times dl. Now, we know what dE is, okay? That's the change in energy between those two large orbits. Now, the assumption here, right? The assumption is that omega does not appreciably change, in an electron going from one large orbit to the next. Okay. And if omega doesn't change, then the energy doesn't appreciably change. Okay. So, well, it changes by very little. Okay. So, but we're going to say omega does not appreciably change. As a matter of fact, we could say that omega is constant, which means that we could write now that we have E is equal to HF, which is equal to H bar omega, okay? And so then that DE is going to be equal to the energy change between those two orbits, okay? Which is nothing more than H bar omega, okay? So the change in energy, right? The change in energy. See if we can make that a little more palatable for you, right? So the change in energy and going from n plus 1 to n for large n is going to be approximately, right? It's going to be approximately, right, h bar omega, okay? And again, assuming that this is constant, okay? Now this would match the orbital frequency, okay? So what we're going to say here is that the energy, right, the energy at these large quantum number orbits, that the energy of that transition is going to be related to the orbital frequency. The orbital frequency, that's going to be the frequency of the emitted electromagnetic radiation. And that's going to be equal to, by the Einstein-Planck relationship, to be h bar omega, okay? So between two adjacent orbits, the infinitesimal change in the energy is just going to be given by h bar omega, which means that we can say then that h bar omega is equal to omega times dl. And lo and behold, right, the omegas cancel. Again, these omegas now are related to the orbital frequencies, okay? These cancel, and we have dl is equal to h bar, okay? So, so given that, then we know that dl is equal to h bar. L then is going to be equal to n times h bar for large n. For large n, Bohr then just made the assumption that what is good for very large n, right? That's that what is good for large n is good at smaller n's. And so that allowed him to lend some credence to the postulate that the angular momentum comes in packets of n times h bar, okay? So the book actually plays a little game on you here, okay? And so I want you to be aware of that. So they actually go back and they put that the change in energy is h bar prime. And then they go then to equate omega prime and omega based on the Einstein-Planck relationship and Maxwell's classical radiation theory, okay? So that's what allows us then to make that cancellation, all right? But if you want to go back and match what we've done with the book, you can put little primes in here, and then again, those omegas then in the limit of very large n become equal, and that's what allows us to cancel them from both sides of the equation, okay? So there you have it. That's the Bohr correspondence principle, still discussed very often in quantum circles. It needs to make sense, right? When you think about it, there should be a very seamless transition, pun intended, in going from a quantum system to a classical system. There are still some issues with the correspondence principle, but we're in 1913 right now, and so Bohr is happy with what he did here. So, okay, that's that. I want you to read the Frank Hertz, the Frank Hertz section. It's just a few paragraphs at the end of that chapter, and then work on the problems. Continue to work the problems, and the next lecture will start with chapter 6. So chapter 6, part 1. All right, folks, have a great night. And, maybe we'll Zoom on Thursday. I have doctor's appointment Thursday morning in which I'm getting tested for COVID. And then after that test, I need to quarantine. So I will most certainly be out of the possibility of visiting campus. So anyway, hopefully I'll talk to the 3 of you on Thursday. All right, take care and have a good evening.